So that's the big room on the second floor. Any questions? All right, it's going to be Monday, April 27th, 6 p.m. to 9 p.m. in the Student Union in room Key West, ABCB. An announcement will also be made on web courses for you guys to take a look at that.
Yep. Okay, so we talked about in depth and how to actually traverse binary trees, but in order to homework assignment that's going to be published today, you actually need to know how to do search, insert. So we're going to go over the search and insert today, and hopefully the delete. Again, as usual, there's code examples up on web courses that are specifically called binary trees, so that you can follow along the source that will help you, and we'll match some of it up in class as well. Okay, so the first thing here is search and insert. So one of the things that I've seen on a lot of the past foundation exams is that you have to code manually how to either do an insert or a delete from a binary tree. So this is very useful. Okay, so we know how to traverse them. What are our two methodologies of traversing? Depth first, so what's the other one? Breadth first. So we either start at the top and go as far left until we find a leaf as possible. So that's your depth first. What are the three types of depth first traversing? Pre-order, in order, and post-order. Okay. From an in-order, a pre-order, in-order, and post-order, how is that relative to the root? When is the root looked at on a pre-order? First. So, first. In order, when is the root node looked at? It's in the middle of your left and your right. And then, so on the post-order, when is the root node looked at? Last. So as long as you can understand those three concepts, it will really help you get through the rest of binary tree. So let's say we want to search for some value. Now, there's two different types of binary trees. There's a binary tree and there's a binary search tree. What is the distinction between a binary tree versus a binary search tree? What makes it an EST?
The left or right?
So I'm hearing stuff about left and right. What's unique today? Relative to what? Right, to the root. Okay, so whatever your value is, your data value that's stored in the root. So in this example here, 8. Everything to the left of 8 will be less than the value of 8. All the nodes must be less than the value of 8. Everything to the right will be greater than 8. You don't have a situation where you would have an equal to 8 because 8 is the root node. So if that's the value you're looking at, you find it immediately as the root and it's ready to be done. But so what makes binary searching trees efficient? What you need to search through on the very first check. If I'm looking for the value of 12, am I going to look at anything on the left of my binary search tree? Why not? Because 12 is greater than 8. So you know it's not on the left. There's no way. Does that make sense? All right, so let's look at this, and we want to look at it programmatically as well. So again, when you do a binary search tree versus just a binary tree, the data has to be sorted properly. And so what we see here is everything on our left is less than 8. Everything on our right is greater than 8. And so again, that's the method of the big O perspective. When you're doing halving, it ends up being log n. So this is one of those things that you're going to need to remember to comprehend when you are doing this manually versus just looking at data. Okay, so binary search tree. We need to make an algorithm so we can write some code. And so the first thing we check to see if the tree is null, because if it's null, then how many nodes are in our tree? Nothing, right? So there's nothing to look at. So it's pretty easy. Otherwise, we need to check the root node. We'll always check the root node first, because we want to see what value is at the root node in order to know what part of our tree we're going to search, or maybe our value is at the root node. So you're going to look at him first. So if the value we're searching for is in the root node, you're done. Otherwise, if the value is less than the value stored in the root node, you're going to recursively search the left. Then it's less than. Use that alliteration to help you remember it. Less than is left. Otherwise, it must be on the right if you fail these first two conditions, because there's no other possibility. It's either equal to, less than, or greater than. Those are all your options when it comes to the logic here. So here we have a function called find, and a return type is int. And the parameter list is defined as taking a struct tree node, so referencing to our tree, and then the value that we're looking for. And then so what we do here, so take that pseudocode and take that. If our current pointer is not null, so that means if it's not null, how many nodes are at least in this tree if it's not null? There's at least one. Okay, so that's cool. So now we can come in here and actually start looking at it. So we know we don't have a null tree, so let's start doing our evaluation. So then what we do is we look at our data in our current position. So the reference you're getting in, just like it was with a linked list, you get the reference, the pointer to the head of a linked list. So in binary trees, in binary search trees, the reference we're getting here is to the root. So it's still at the beginning. The structure is different, but the concepts are the same. You've got to find that location where the reference is ending up. Because just like in a linked list, if you lose your reference to your head in linked list, you've lost the whole thing, right? If you blow it out of the water and you're like, oh crap, I've lost everything. Same thing is true here with the root node of a tree. You got to know where you're at, otherwise you lose your whole tree. So we go through here, and we find out that it's not null. So then we're going to look at our data. Is the value stored at the root node, the data piece of it, does it equal the value we're looking for? If that comes out true, then we're just going to return 1, because with our int return type here, a 1 indicates that we found it, a 0 indicates that we didn't. Just go back and face this binary. 0 is off and 1 is on, or 0 is false and 1 is true. So then here, first we're going to search to the left. So we're going to check and see if the value passed in is less than the data currently stored at the root node. If that's true, we're using recursion to keep checking. So this is another good implementation of recursion. We can use them in binary trees, because we just need to keep checking for every node in that tree. So if we come back and this is true, then we are saying that the value I'm looking at is less than my root node the first time through. So then we do a return, and we call ourselves again. And we're going to check to see if the value we're looking for is in the next node. And we're referencing that next node right here. Current pointer left. What is that left? Without even looking at this code, we looked at a basic struct all last week. What would our left be? The left child of the root node. Does that make sense? It's just kind of like the next on a linked list. Now we actually kind of have two of them. We have one that's on the left and we have one that's on the right. So this is just like next on a linked list, except we're going to the left. You should remember, on a binary search tree, if the value is less than the root, it has to be on the left, because that's how binary search trees are established. So here, we're just going to use recursion to keep looking until we get depth first on our left, until we no longer find this no longer comes back true. So once we get a false evaluation for if that was less than the data that's stored at my current node, then I'm going to keep looking. Here, if it's not equal to and it's not less, then it must be what? That is to the right. We don't have any other choice. So here, we can use recursion again, except this time we're going to the right, because if it's greater than, it's on the right side of our root. Does that make sense? Okay. simply searching for a value in our tree. And it will follow the appropriate path based on the data that is stored in our BST. So again, let's say we're looking for the value of 7. The first time we come in here, we're going to check 7 against 8. Do they equal each other? No. Is 7 less than 8? Yes. So that says, when I call that function find again, it's going to pass a reference to this class. So the node is now going to be the value of 3 that gets passed into our recursion. So now we're comparing 3 and 7. Does 7 equal 3? No. Is 7 less than 3? No. So we have exhausted the equals, we've exhausted the less than, so now we know it must be, the value must go on the right of our tree. So we call our function again. Here. So we come in here, and now we've passed the right of our 3 and our value 7. We come in here, we look at the right value. Our right value is 6. Is 7 equal to 6? No. 7 less than 6? No. So it must be the right. We are if or else isn't or else. It must be on the right. So when we call that function again, now we're calling this version of it right here. We pass the right and our val 7. So now we have a reference to this node right here. Is 7 equal to 7? Yes, we found it. We're like, woo, found our value. Okay? So, in a sense, this is our base case where we actually found the value. And now we can talk about our recursion. Is there a recursive function call on that if flag? I don't see one. I just see a return 1. But is there a recursive function call in the if else? The if here, is there a recursive function call?
Yes.
How about the else? So both of these have recursive function calls. The first if check does not. That's what makes it a base case. That's when we stop stacking recursive function calls on top of each other. Remember with linked lists, you're always looking for that base case. How do you get to the point? When we're dealing with recursion, there's always that base case that stops the recursive function call. In this case, it's stopping with the recursive function call to match our value. Now, if we match it here, and then we go, okay, we are absolutely done because we get to return our 1. So now we're done with our recursion and we can get out of this function. Does that make sense? So just like when we're first talking about recursion, we're using it again here to find a certain value in our binary search tree. How do we actually create a binary search tree? So we have to insert through. Null, right? So just like the linked list, you have a head and each one is null before you even create your linked list. So I would do the same thing in a binary search tree. Remember, binary search tree means that what? What's about the data in a binary search tree? Relative to the root node. Everything to the left is less than that value. Everything to the right is greater than that value. So how do we actually do this? All right, so here we need a struct. Again, this is just showing you our struct. We have our data portion, and then in this case, we have 2 pointers, one to the left and one to the right. And so we need to go ahead and actually create this. So in our main function, we're just going to create an instance of our binary, of our root node here. And so this is the root of our tree. So just like your linked list, do not lose this reference. Because if you lose the reference to the root node of your binary tree, you're going to lose the entire thing. Just like with a linked list, and if you lose its head. Same concept. So now we need to know what data we're supposed to put in there. So in this case, just like with linked lists, we set our data, we set our left, and we set our right. So here, when you see a left being set to null and a right being set to null, What is that indicative of when you're dealing with like lists? What does that tell you? You're at the end, right? So in this case, that's going to mean that we found the leaf nodes. Remember we were talking about the leaf node? We drilled down as far as we could with the down first. We go all the way to the left until we find a leaf node. What makes it a leaf node? What doesn't it have? It doesn't have children. So just like with a linked list, once you find that null, you're at the end. In this case here, when you find a null on your left and your right, you know you found a leaf node. And you're at as far down as you go in the tree. Does that make sense? It's the same concept. So here, when you're creating each one of your nodes, first, don't forget to do your malloc, because just because you declare it up here, you create an instance of it called temp. You don't malloc, and then you start messing with the data, you're going to get null pointer errors. Okay, so set up your data, and then we want to make sure that you set up the left and the right as null when you first initialize it. So this, and then you just return that back. So there's two different ways to talk about this. When I had you do assignment 2, I asked you specifically not to use a global head. To use a header, head that you have to pass back and forth between the functions, or you can use a double pointer. So one of the things I learned from a root during the foundation exam review is that he doesn't like dealing with double pointers. So I just want to make sure that when you are understanding how to do linked lists and binary search trees, when you're passing a reference where the head of that linked list is, or where the root of the binary search tree is, you understand how to pass it back and forth. So in this case here, we see that our return type is a struct type true node and it's a pointer to it. So when you want to return back and forth between functions, the head of a linked list or the root node of our binary search tree, that's how you would pass that reference back. So for people who are not at all comfortable with double pointers, this is your other option. Okay, just so you know that. All right, so we need to create a BSC. So most important thing about BSC is that their ordering property is laid out in very specific format. So right here, when we start to insert, we have to follow these specific rules. So you start at the root, and either you're going to go to your left or to your right, depending upon the value that you're trying to insert, relative to the data value of your root is. And you keep going until you find an empty position. How do I know I found an empty position on the left or the right? What's it going to equal to? No. That's how you know. Does that make sense? Just like a linked list. That's why we stick so much on a linked list, because it really does roll forward into everything that we're doing here. Okay. So what will happen is you'll be given a series of values, and you'll be asked to create a binary tree or a binary search tree, depending upon what the task says. So make sure you pay attention to whether or not you're being asked to do just a binary tree, or you're specifically being asked to do a BSC, because you can get a entirely different result if you are not doing a BSC. So here, this is, we have to do these in their order. And so from the homework perspective, I'll give you a series of data, read them all the data in, and you've got to plop it into a binary search tree, or just shove it into a regular tree binary. But anyway, so the very first value will be indicative of our root. Okay? So that we have to create our root node. So when we create our root node, what are we going to set the data portion of our struct to? So there's 3 pieces to our struct. There's the data, the left, and the right. We have our first value here, 10. Where is it? What do we do with that? As far as the struct is concerned. We're going to set it to the data portion, right? So here's our data, so that's where you're going to store that 10. So you create that node, set the data portion of it to 10, and then we're going to do what with our left and our right pointers? Set them a null, because we created our node. Every time you create a node, set the left and the right to a null when you're creating a binary search tree from scratch. All right, so our next value is going to be a 14. Come back here. Now we have a 14. So we create our node with a 14, and now we have to do something extra. because he's not the root. So we're going to do what? You're going to compare the 14 to the value of the root node, correct? Is it greater than or less than? Greater than. So it goes to the right. So now we need to update our pointer on our root node and set his right equal to this new node that we just created for 14 so that we can link them together. We have 6. So what do we do first? Create our node. Set the data value of 6. Now what?
Compare.
You're going to compare it to 10, correct? What's the result going to be? It's less than. So what are we going to do to our root node? Or set his left where you go here, 6, correct? Does that make sense? Okay, so it's just like white slice and stuff, we're just putting them in this different order. Yes, sir. Yes, absolutely. For every node that we create, the first thing we're going to do is set its data value and set its left and its right to a null. Assume that it's going to be at the end, unless we otherwise know better once we do the evaluation. Does that make sense? So just like with the linked list, when you knew that you were going to put that node at the end of your linked list, what did you set its max equal to? You set it to null, because you're at the end. We want to do the same thing here, and now we have 2 pointers instead of 1. We have our left and our right. Now we have 2. So we create that node, set our left and our right to null. Now we compare it to the root. It's less than the root. Does the root have a child? On the left, it does. So we want to look at that child, because whatever that child is on 6, we need to know what his value is. So now we're going to compare our 2 to the value. And the 2 is less than 6, so we need to go to the left. Before we set up our pointers, we want to check to see if 6 has a left already established. If it's left equal to null or not. If it's equal to null, we know we found the leftmost root, the leftmost node in our tree, in our binary search tree, so we know we can just throw our 2 right there. If there was another value, we would keep going. Yes, sir?
What would happen if we do the data error and it would be the same, the tree like the same this one, put a 6, what would happen to that? Once the 6 is already good,
Then it's not a valid binary search tree. So, because you would find where you're equal, like, that would pretty much have to work. It wouldn't be a binary search tree. So if you've got a problem, if you're given a series of data and you said, and there's 2 instances of 10, you're just going to go, I can't. This doesn't work. Binary search trees are very specific in their structure. Either less than or greater than the value of some node. You can't have equal to. The only time we want equal to in a binary search tree is if you're looking specifically for that data value. So if you're trying to add it in there. So in this case, if you don't put code in your application to account for the fact that maybe, just maybe, somebody gave you bad data, and you have to do something with it. So having your program just crash probably isn't very ideal, right? So the correct implementation from a good programming practice would be to put a condition in there that handles if the data is equal. And then somewhere along the line, someone will tell you, well, if the data values are equal, then you can either just throw that node on the floor because you don't care, or bring attention to the user that you found duplicate data in the binary search tree, and that can't happen. That's not valid. So it just depends on what guidance you are given, what to do with that duplicates. And that just depends on who's giving you information, what the purpose of it is. But good programming practice, you would handle the situation where we found it equal, because it's not right. The data is incorrect if you find that equal. Does that make sense? So it just depends on how you write the code. So here, now we do the same thing with our 5. Our 5 is definitely less than 10. Our 5 is definitely less than 6. And then 6 has a left. So we can't put it where the 2 is at because it's already occupied. So then we and relative to the 2, the 5 is actually greater than the 2, and therefore you would put it on his right. And then we follow the same process for our 15 and our 17. Our 15 is going to go to the right, and 15 is greater than 14, so that's going to go to the right as well. And then finally 17 comes in here, and he's greater than 15, so he's going to go all the way to the right as well. So when you're doing an insertion into a binary search tree, so wait a minute, all we did here is we just created it with our data. Now let's talk about what happens if you get a new node that goes somewhere in the middle. So if it's empty, just do the you just create it. If your tree is empty, just like with the linked list, so when you got your data in and if your head was null, then you just set it equal to that new node temp. Because they were equal. It was the only node in the linked list, same thing with the tree. Otherwise, you have to figure out how to insert this guy. So how do we do that without making a big huge mess out of this thing? So here we do our insert, and first and second C were null, because if we're null, we know that this is my root node at this point in time. Otherwise, now you have to check to see where it goes. It says here, so the element should be inserted to the right. So if our element of data is greater than the root data, then we're going to set our root right equal to an insert of that data itself. Otherwise, we know that it's less than, so we go to the insert on the left, and then we update that. So that part of it makes it pretty easy. And so we can just create our binary search tree in this order. And so you just keep creating these nodes until you are finished and you've exhausted all of your. Woo, that's killer. Oh my gosh. So when you're doing that, here's the code that's up on web courses. Okay, so here's my binary tree. I have my data, I have my right, and I have my left. And there's 3 reference called bin tree node here. And then I do my insert. Now here, we're using double pointer notation. So when you are using double pointer notation, you have to make sure you dereference that node before you try to use it. So when you're using double pointer notation, you need to get one of those pointers off of it. So it's just the same way as when you are trying to access the data of something that is a pointer. So like if we had a character and you want to get the data off of it, you dereference it. So we have to do the same thing here. So we have to dereference this guy so we have a single pointer. And then what we're going to do is we create our temp, and we're going to set it equal to, we're going to mallet for him, and then we're going to set our left equal to our right, which are both null. So this is just creating the node. It's just a condensed format, and then we set our data on line 19 to the value that's passed in, and then we set our tree equal to our temp. So when you come down here in our main, so here's the root. So just like the head with the linked list, here's our root, and then I want to add to my root a series of numbers, a series of values here. Now remember, when you're using double pointer notation, at this point, root on line 103, is that a single pointer or a double pointer? It's a single. Because if you look at the declaration up on line 99, there's just one asterisk. So we're trying to pass it as a double pointer. So we needed to have 2 asterisks in front of it. So that's why you do the ampersand. The ampersand gives it another address up. So that's what turns it into a double pointer. Yeah.
The binary tree in the node is 9 or 10. If we set a value like 7 or 10, how do we know if it goes on the right or 6 or the left or somewhere in the map?
Okay, so we have our series of data. We say that the first value is the root. Okay? And then, if the root's value is 10, on a binary search tree, everything to the left must be what relative to 10? Less than. So our next value is 14. Where's that going to go? It's going to go to the right. Why is it going to go to the right? Yes. So we use answer to our question. Just whatever the root node is, it's relative to the root node. So even if it has value on here, if I got the value of 25, I'm going to compare that to the value of 10 in my root node. What does that tell me? Yes. The root is creating the binary split between the left and the right, the left and the right hand. Does that make sense? Okay, so here is some sample code of my web courses that shows you how to create a binary tree with a series of values. And we're specifically doing a binary tree, binary search tree. So when we come up here, we can have all of our different printing options here, and then we can also delete our tree. So there's a lot of code going on here in this example online. So we just have a simple insert function, and we'll just want to create our node, do our malloc. When we create a node, we always have the left and the right and null. So that's what's going on in line 17. We say our left is equal to our right, and they're all equal to null. We set the data, and then we just return back our tree in this case. Now, so this is checking to see if our tree is empty. So if we come down here, our tree is not empty. So this is where we're looking to see where we put this node. If our tree is not empty, then we know that we have an existing tree that we need to put our node into. So now that we start checking the data. So on the tree sub data is our value less than what it is. And if it is, then we go ahead and say insert and insert into our left. If it's not, if our value is greater than the value stored in the root node in that tree, then we're going to go ahead and insert on the right. And this is actually a recursive function call if you look at it, because it's going to keep checking. And what it's looking for is what? What do we keep looking for each node as we try to insert a new node? We're looking for the end, right? We need to figure out where it's supposed to go. So we keep looking at our data node by node. So the code that shows insert includes the recursive function call. We keep looking to the left if it's less than, and to the right if it's greater than, to find the end. So how do you know 5 and 17 are leaves? Their left and their right are equal to null. You know that's the end. Does that make sense? That's what we're looking for. This code is recursively calling insert until it finds the end, right here, on line 26 and line 28. It's looking for the end on both the right and the left. Where do I put this node? That's what this code is doing. Does that make sense to you guys? We just keep looking. It's just like when we're looking for the base case. What's our base case? Both of our left and our right are null. That's our base case. We know we're at the end. We found the end of our tree, so now we can add a node. Okay, so here's one thing you can do with that you may be fortunate with. Here's sum all the nodes of the binary search tree. So how would you actually do that? So, with linked lister is pretty easy because you could just continue walking through your linked list until you found next equal to null, then you found the end of it, and you're done. How do we do that in the binary search tree? So here, what we do is we just add the values of our root on left and the right, and then return the answer. Again, here, recursion is doing this for us. So we can write a much simpler implementation. Think about when we first talked about linked lists and summing the squares into those values. And recursion, we first started about recursion. You know, so the first time through, it started at the value of 1. But 1 was not our base case. So then we get 2. 2 was on our base case. So we kept stacking those add function calls on top of each other until we got to the value of 10. 10 was our base case, so we needed to quit. And so then we actually started going through and compiling all of the data or doing the math on the powers of 1 through 10 based on that stacked function calls. So here we're really doing the same thing, except instead of just in a single linear fashion, we're actually going doing the left and the right. So here, look. Remember that one example I showed you where with recursion you could do going up, going down, or split it in half. So half of it was going down, the other half was going up, and you added them all together. That's what we're doing here. It drives us forward to this example, where we're doing it basically splitting it in half. That's what binary trees do for us, is it splits it in half. And so here, what we do is we call our functions add again with the left, and then add to our right. So for every node, it's going to try to add another value. So what is this null telling us? Why are you checking for a null? What is that telling you about the current node? We're at the end, right? We're finished. This guy's left is equal to what? What is the value of the pointer on 2's left?
Null.
It's null. That's how you know you're done, because you found the end. So in this case, null is your base case that says, hey, we're out of here. But when he looks at his right, he goes, oh, I still got another guy to go, so I need to call that recursive function call again. So I want to add this value of 5 in there. I don't want to lose it. So then when you get to the 5, and you look at his left and his right, then we're done. So we can start actually taking care of each one of those recursive function calls and do the math and do the addition on it. So the code is pretty short and sweet. But what it includes in it is it's going to take the data of the current pointer, and it's going to add the data of the current node's left and the data of the current node's right. And then it keeps checking for each left and right if they are null. And it does that in a recursive manner. So walk through it all. All right, so we're talking about binary search trees, and that's really awesome. But what if our data is actually not ordered? But you're searching for some value. So how are we going to deal with this? So there's a different way to deal with that. And we still do look on the left and the right. Just like they're doing the summing, we do our recursive function calls, we're doing the same thing here. So we're just going to look at our current pointer, and we have our data value. And if it's equal to the value we're searching for, we have our base case, and so we're done. We can return back that 1 that we found the value. Otherwise, we need to return back searching its left and its right, because we don't know. If it's just a binary tree, it's not in any specific order. So you have to check the left and the right for each one, because you don't know where it's at in the binary tree. And so that's what this function right here is doing for you, is that it's going to check the left and the right on every node that you visit. So if we look at this from our code example, so we look at the insert, here's our search, okay? So we come in here, we receive a double pointer to the root node and the value we're looking for, and then we return back just a reference to our node. And so first we make sure that the tree's not null, because if it is null, then there's nothing to search, right? There's nothing there, so why are we searching? Otherwise, if we get past that line, if we don't have an empty tree, then we need to start looking at our data. If the value that we're searching for is less than the value of the root node, the data, we're going to go to the left. If it's greater than, we're going to go to the right. So remember, this is very specific. to being a binary tree. So this is specifically code for a binary tree. And how can you tell that this is specific to a binary tree? Besides the fact that I'm telling you that. The left and the right searching are not being called simultaneously. They're independent. You're specifically looking on just the left or the right. Whereas what we're looking at here in my slides that I closed. This example right here it goes to the left and to the right. So this is searching just any binary tree. Doesn't have to be specifically a binary search tree or ESC. And you know that because it doesn't care if the value is less than or greater than the current node. Doesn't care. But it could be anything in a regular tree. Yes, sir.
Thank you. Something else that my phone on your return.
You're right, I am. Thank you. So this is indicative of just searching a non-sorted tree. And you know the difference because here is specifically looking for the left and the right. You guys see the difference between those two functions? So that's something you need to be able to identify. Is this a binary search tree function, or is this just a search function? And this one here is binary. Search tree, or EST. Whereas this one right here is not. There's no data for it. Okay? Okay. So assignment 4 is going to get published today. Definitely go get this code example from Web Courses. It will help you survive that assignment. And then on Wednesday, we'll talk about